In this next series of videos, what we'll do is we'll use our newfound knowledge of the enthalpy of reaction and how to calculate it in order to solve material and energy balance problems. The problems that we'll solve are listed in the Chapter 9 Lecture Problems worksheet that you could find on the Canvas homepage. And I chose a selection of problems that cover a sort of diverse variety of different processes. And so even though these processes are very distinct from one another, what I'll show is that you could use the same sort of strategy that I outlined previously in order to solve these problems. So let's begin with problem 1. Problem 1 deals with fuel cells. Now you may have heard the word fuel cell thrown around quite frequently. There's significant amounts of research put into developing fuel cell technology. But what exactly is a fuel cell? And so that's what I want to demonstrate with this problem. And so a fuel cell, to simplify it, is just a sort of continuously operating chemical device that uses some sort of fuel and reacts that fuel with oxygen in order to produce electricity. So it's similar to a combustion reaction where you have some sort of fuel and you combust it with oxygen to form carbon dioxide and water. But with a fuel cell, what you produce instead is electricity and water. And so because you're not producing that carbon dioxide, the use of a fuel cell is a cleaner way to produce energy than just doing regular combustion. All right? And so what's going on in this fuel cell device is we have a fuel, so our H2 fuel here, and it's being fed into the system. And this fuel then reacts with this porous anode in order to form 2 electrons and 2 protons here, the H pluses. These electrons travel from the anode through this current all the way to the cathode. And as they travel through this, or not through this current, through this circuit, and as they travel through this circuit, they create a voltage potential drop as well. And this circuit also has some sort of resistance. And as you know from Physics 2, anytime you have a voltage and a resistance, you also create a current. And so you could use this current in order to provide electric work. All right? In any case, these electrons travel to the cathode where they then react with oxygen that's being fed into the system. And so these electrons, along with the oxygen, react to form, or the protons react with the hydrogen, or the protons react with the oxygen in order to form water, which you see here. Okay? And so that's the basic type of outline of how a fuel cell works. All right? And for this particular fuel cell, you'll see that it operates at 85 degrees Celsius. And so based on this outline, what this problem is asking us to do is it's asking us if stoichiometric amounts of hydrogen and oxygen are fed into our fuel cell, and we know the conversion of the hydrogen, which is 0.65. The problem is asking us how many kilowatt hours of electric work can be obtained from the cell per moles of hydrogen fed. Okay? And so at this point, what I want you to do is I want you to pause the video, and I want you to think about, try and gather as much information as you can from this problem statement, and then convert that information into a process flow diagram that's fully labeled. Okay? And then I want you to identify the information that you know and the information that you don't know. Okay? So pause the video right now and do that. Let's continue. And so the way we could think about this system, based on the information that was provided describing how fuel cells work, is we could sort of draw our system boundaries here and say that we have a system where H2 fuel and oxygen are being fed into the system, and what's being produced is a stream of water and also a stream of electric work, which I'll abbreviate as WE here. Okay? And so that's sort of how we could simplify down the process and how we could sort of imagine it. And that will allow us to, facilitate the solving this material balance problem, material and energy balance problem. Okay? And so, based on the information in the problem statement, you should have been able to develop a flow diagram that looks like this. Okay? And so for this problem, since it didn't really outright state what the basis was, and since it wants in the end, it wants the electric work that's produced from the system to be in units of kilowatt hours per mole, what we could do is we could choose for our basis just 1 mole per second. Okay? That should not affect the final answer that we get, since we are just going to be taking a ratio of the electric work per the moles of hydrogen fed. Okay? In any case, what we have right now in stream 1 is we have 1 mole of hydrogen being fed in. In stream 2, what we have, since we know that the hydrogen and oxygen are fed into stoichiometric amounts, that means we have 0.5 moles of oxygen being fed in. And both the hydrogen and the oxygen are being fed in at 25 degrees Celsius. Okay? In the outlet stream, in stream 3, the temperature, since the problem tells us that the fuel cell operates at 85 degrees Celsius, the temperature is now 85 degrees C. And we also know that the fractional conversion of the hydrogen is 0.65. So I put that information there. What we don't know about the system is we don't know the flow rate of stream 3. We don't know its composition either. We don't know how much hydrogen it has or how much oxygen there is. We also don't know how much water was produced. But we do know that the mole fraction water, since there's 3 components here, we could just get that based on knowledge of the compositions of the hydrogen gas and the oxygen as well. Okay? The other thing we don't know is the electric work that's being emitted from the system. So this W sub E here. All right? And so everything in red is our unknowns. All right? As far as the reactions are concerned, based on the description of the process, we could extract 2 types of reactions that are occurring in the system. So at the anode, what's going on is we have the hydrogen fuel. It reacts with the anode to form the 2 protons and the 2 electrons. And then at the cathode, what we have is we have the oxygen reacts with both the protons and the electrons in order to form H2O. All right? Now, what we could do here is we could add these 2 reactions together, right, to get some sort of reaction C. And if we add them together, what we get in the end is we get a hydrogen gas plus a half a mole of O2 gas. And on the left-hand side, we see that both the protons and the electrons are both on the left and the right-hand side. So those things cancel out. And so we're left with, on the right-hand side, is just H2O liquid. All right? And so this is our overall reaction for the process. Okay? And really, the only thing we care about is we only care about this overall reaction. Right? Because this overall reaction contains chemical species that we could easily look up in tables. You know, we have information about H2 gas, O2 gas, and also H2O liquid. Right? So as we proceed, we're actually just going to treat it as if we just are dealing with this reaction C. All right? So at this point, we know what our knowns and our unknowns are. What I'm also going to do at this point is prepare an enthalpy table. I won't fill in the references yet, but I'm just going to go through and just prepare what that table will look like. So we have our different species, and we only have 3. Right? We're going to need a column with all the moles that are coming in, and that's going to be in units of moles per second. We're going to need a column of the enthalpy of the stuff coming in. And that's going to be in terms of kilojoule per mole. And then we also need a column of the stuff coming out. And then a column for the enthalpy of stuff coming out, which will also be in kilojoule per mole. All right. And so at this point, we have identified what all the information that we know, and we've identified the information that we don't know. And so what we should do now is a degree of freedom analysis to determine if we have enough information to solve for all our unknowns. And since we're dealing with reactions now, rather than doing a molecular degree of freedom analysis, what we're going to do now is an extent of reaction degree of freedom analysis. Okay? And so what I want you to do now is I want you to pause the video, and I want you to think about how you would do a degree of freedom analysis for an extent of reaction sort of material balance. Okay, so let's complete this degree of freedom analysis. Now, for an extent of reaction type of degree of freedom analysis, the first step is the same as the molecular one. So we count up our unknowns. And so we have 4 unknowns. We don't know what the flow rate of the outlet stream is. We don't know the composition of the H2 or the O2 in that outlet stream. We also don't know the H2O composition, but we know that's dependent on both the hydrogen and the oxygen compositions. And the last thing we don't know is the electric work that's provided by the fuel cell. So we count up our unknowns. The main new step with an extent of reaction sort of degree of freedom analysis is now we need to count up the number of independent reactions we have. Okay? And since we only care about the overall reaction in our system, we could just say we have one independent reaction that we're going to look at. We're not going to do anything with the electrons or the protons, right? So we're not going to consider reaction A or B. We'll just consider that net overall reaction. The number of independent species we have in the system is 3. The hydrogen, the oxygen, and the water are all separate species. And the other equations or pieces of information that we could use totals up to 2, because once again we still have our energy balance that we could use, and we're also given information about the conversion of the hydrogen in the system, and so that's going to be useful later on. And so when we calculate the degrees of freedom, what we do is we take the number of unknowns, we add on the number of independent reactions we have, and then we subtract off the independent species and the independent or the other equations that we have, and we get a degree of freedom of 0. So we could solve for all the unknowns in our system. And so once we do that, once we identify that we have enough information to solve the unknowns, let's now proceed to our material balance. Let's start with the hydrogen. So H2 material balance. And so even though we're dealing with reactions, we're still going to start with the general reaction equation. But now let's go slower here, right? Because unlike the non-reactive systems, we now need to think carefully about what each of these terms stands for. Okay, so with accumulation, we're still dealing with steady state systems, so that part's going to be still 0. All right, and now for this H2 system, let's think about it. We do have an input stream. We do know that not all of the hydrogens reacted, so some of it will be in that stream 3, so we do have an outlet. We know that nothing is generating hydrogen in this reaction, so the generation term is going to be equal to 0. But we do know that hydrogen is being consumed in the system. It does participate in the reaction. So we do know that there is a consumption term. And so if we take all the non-zero terms and rearrange them, what we get is that the input is equal to the output plus the consumption. Okay? So let's think about what each of these terms is going to be. So for the input, that's just going to be equal to the molar flow rate of stream 1, since that stream 1 is just completely hydrogen, and that's the only source of incoming hydrogen into the system. For the output, this is going to be the hydrogen that's leaving in stream 3. So we know that this is going to be equal to the total molar flow rate of stream 3 times the mole fraction of the hydrogen in that system. Now for the consumption term, we could define this two different ways. The first way we'll define it will be as a function of the extent of reaction. Okay? And so the consumption in terms of the extent of reaction is going to be equal to the magnitude of the stoichiometric coefficient for hydrogen in our net overall reaction. And that's multiplied by the extent of reaction. Another way we could define the consumption term is we could define it in terms of the fractional conversion of the hydrogen gas. And so this is going to be equal to N1, which is the flow rate of the hydrogen gas being fed into the system, times that fractional conversion. All right? And so I won't pause the video here, but I do want you to think about why the consumption term is equal to these two different equations. In any case, since we have this relationship for the consumption term, and the only thing we don't know here is this extent of reaction. Actually, I'll circle it in red to be consistent. What we could do is we could rearrange those terms in order to solve for our extent of reaction. Since we know later on, once we start dealing with the enthalpy of reaction, we need to know what that extent of reaction is. Okay? Right? And so we can rearrange the equation so that we say that the extent of reaction is just equal to this relationship. And if we plug in all the values, so what we have is, well, actually, this consumption term here should be the new dot in order for the units to be consistent, since we're dealing with an open system. All right, and so what we have here is we know our basis is 1 mole per second. In that reaction, the stoichiometric coefficient for the hydrogen is negative 1 mole per second. But we're looking at the magnitude, so that negative sign goes away. And then the overall conversion was equal to 0.65. All right. So in the end, our extent of reaction is just 0.65. Now that we have this information, we could go back to our hydrogen material balance and really now that we figured out what the extent of reaction was, the only term that's left unknown in our material balance is the product of the stream 3 flow rate and the mole fraction of the hydrogen in that flow rate. We could rearrange, well, first we could just call this just the flow rate of hydrogen in stream 3. And if we rearrange our material balance, what we get is that flow rate of hydrogen in stream 3 is just equal to the input minus the consumption term. And the only unknown we have here is this. And so if we plug in all the values, you should get a number of this. So 1 minus 0.65 gives you 0.35. Okay? Let's now proceed to the next species on our list, oxygen. And let's go through its material balance. Alright, and let's start identifying which terms are negligible. So once again, accumulation, we could say is 0 because the system's at steady state. We do have an input of oxygen into the system. All of stream 2 is oxygen. We do have an output. There is oxygen in stream 3. No oxygen is being generated, so we could say that's 0. But we do know that oxygen is being consumed in the reaction. Alright. So once again, similar to the hydrogen material balance, our oxygen material balance is that the input is equal to the output plus the consumption. Okay? As far as what each of those terms are, the input is just equal to the molar flow rate of stream 2. The output, we could say, is just the molar flow rate of oxygen in stream 3. So we'll combine the mole fraction and the overall flow rate for stream 3 there. And then the consumption term here is once again the stoichiometric coefficient rate for oxygen times the extent of reaction. All right. And so here, in our overall reaction, if you go back and look, you'll see that the stoichiometric coefficient is equal to -1/2 moles per second here. And our extent of reaction, which we solved for previously, is 0.65. And so what we get is 0.325 moles per second. Okay? All right, and so now that we have this material balance, what we could do is we could rearrange the material balance. And really the only unknown we have left is the oxygen flow rate in stream 3. And we know that it's just going to be equal to N2 minus this stuff. Right? And if you plug in the values, what you should get at the end is 0.175 moles per second. Let's now complete the material balance for our last species, the water. We once again start with that general equation. Alright, the system's still steady state, so that's 0. We don't feed in any water into the system, so the input stream is equal to 0. We do have water leaving the system, the output. Water is generated, so our generation term stays, but water isn't consumed, so our consumption term is also equal to 0. And so what we get here from this relationship is that the generation is just equal to the output. So let's figure out what each of these terms are, or is. And so generation, it's still the same, similar to the consumption terms that we had for the hydrogen and the oxygen, is we have the magnitude of the stoichiometric coefficient rate for the water in the reaction, and that's times the extent of reaction. And based on reaction C, what we know is that in this reaction, 1 mole per second of water is produced, and that's going to be multiplied by 0.65, and that gives us 0.65 moles per second. And from the material balance, we know that's equal to the output stream, and in our output stream, that means that the water in the 3 stream is equal to 0.65. Alright, so we solve for all the molar flow rates in our system, and so let's go back to our enthalpy table and put those values in there. Okay. And so in our enthalpy table, we know that we had 1 mole per second of hydrogen gas being fed in, 0.65 of oxygen being fed in, and there's no water being fed in. Okay. Now, for the stuff coming out, we know that 0.35 moles per second of hydrogen gas is coming out, 0.175 of oxygen is coming out, and 0.65 moles of water is also coming out. Okay? So by solving the material balances, we could fill in these sections of our enthalpy table. Okay? At this point, now that we're at the enthalpy table, the next step for solving our energy balance problem isn't to jump directly to the energy balance yet, but instead to figure out what the change in enthalpy of our system is. And since we're dealing with enthalpy, we need to start thinking about what our reference states are. All right? Because we're going to be dealing with a reaction, and a lot of the information we're going to be looking up is going to involve reaction conditions at 25 degrees Celsius and 1 atm. What I'm going to do is I'm going to set our references for each of our species to be at that temperature of 25 degrees Celsius and at that pressure of 1 atm. And so for H2, we're going to say the reference phase is a gas, and the temperature is 25 C, and the pressure is 1 atm. And same thing for the oxygen. And then for the water, the reference phase is going to be a liquid instead, but it's still going to be at 25 C and 1 atm. Okay? And I'm doing this because, as we saw when you learned about the heat of formation and heat of combustion, when you look up those values in the back of the book, those are all going to be at 25 degrees C and 1 atm. And so I'm anticipating doing that calculation. And so that's why I'm setting these references to be at that temperature and that pressure. Okay? All right. So let's go back. All right. And what I'm going to write out here is I'm going to say, let's now focus on calculating the change of enthalpy of our system. But in order to do that, first we need to figure out what the enthalpy of reaction is for this reaction. And specifically the one at the standard state. Okay? All right. And so to do that, I'll say let's first calculate our standard delta HR, and I'll write out the conditions at 25 C and 1 atm. And at this point, you could pick any method that you want. You could use the heat combustion method or the heat of formation method. And for now, I'll just show an example of doing the heat of formation method. And you'll see why this one, it kind of makes the calculations easier. And I'll point out why in a bit. Okay? All right. And so to calculate the standard heat of reaction in terms of the heat of formations, let's use one of the equations that we defined in the previous videos. right? And so we know that the standard enthalpy of reaction is equal to the sum of the products of the stoichiometric coefficient for everything times the heat of formation for the species. And here you subtract off the reactants. You use the stoichiometric coefficient and also the standard enthalpy of formation. All right? So let's expand out what this equation would be for our system. And so for our products, the only thing we have is the water in the reaction. And once again, so we're just thinking strictly in terms of the reaction. Even though our stream contains oxygen and hydrogen, when we're calculating the standard enthalpy of reaction, we're just looking at only the products of the reaction. Okay. So here, H2O, the heat of formation of H2O, liquid, I should specify. And then we're going to subtract off all the reactants. So here we have hydrogen, heat formation of hydrogen, plus oxygen, O2. Okay. Okay, so to solve for the standard enthalpy reaction, we need to know what the enthalpy of formation for water, hydrogen gas, and oxygen gas are. All right? But there's a reason why I picked doing the enthalpy of formation method for this problem. And it's one thing that you could think about when you're attacking these problems is in our reactant stream, we're dealing with H2 gas and O2 gas. So those are elemental species, right? And as we know, for elemental species, by definition, their enthalpy of formations are equal to 0. Okay? And so what that tells us is that our standard enthalpy reaction is actually just equal to this. Liquid. All right. All right, and so that's one little sort of trick you could do in order to make your calculations easier, is if you're dealing with a reaction that involves a lot of elemental species, so, H2 gas, O2 gas, or, nitrogen gas, or even, carbon, or solids, or, silicon solids. If you do the heat of formation method to calculate the enthalpy reaction, you could get rid of a lot of those terms pretty quickly, because those values are going to be equal. The elemental species are going to be equal to 0. Okay? In any case, so what we need to do now in order to calculate the standard enthalpy reaction is we just need to look up the enthalpy of formation for water. All right? And you can look that up in table B1. And so what I want you to do now is I want you to pause the video and I want you to look up the enthalpy of formation for liquid water. From table B1, what you should have found is that the enthalpy of formation for liquid water, or the standard enthalpy of formation, is equal to negative 285.84 kilojoules. And you have to be careful. You have to make sure you looked up the value for the liquid water, not the vapor water or the gaseous water, because that's a different value. And remember, that takes into account the enthalpy of vaporization. All right, so we want to look up the value for liquid water. All right, and so this was our enthalpy of formation for liquid water. So that tells us our standard enthalpy of reaction is equal to the stoichiometric coefficient of water in our reaction, which was 1 mole, and the delta H of R, which is negative 285.84 kilojoules. And so 1 times that gives you the same number back. So this is the standard enthalpy of reaction. All right. But what we have to remember is we're working with a continuous system here, right? And so what we really want is not just the standard delta HR, but we want the standard delta HR dot. All right? And the formula for that was delta HR, the standard delta HR, times that bracketed term, which was the stoichiometric coefficient rate for water in the reaction divided by the stoichiometric coefficient. All right, and so really, I mean, what you're going to be multiplying again is you're just taking your value and you're multiplying it essentially by the number 1. But the reason we do this is because we want the units to be consistent, because these moles will cancel out, and what you're left with is an energy rate. Okay? So that's what our standard delta H R dot is. All right, so now that we have this value, we could calculate the total delta H dot for the system. All right, and so let's now calculate for entire process. Okay. So our delta H dot, in order to calculate that, we could use the equation we defined before. And so we're going to use our heat of reaction method. And so what we're going to do is we're first going to account for the reaction in our process. And that's handled by this product of the extent of reaction times the standard delta HR dot for a reaction. And then we add on the actual enthalpies of each of our species. So first the products, and then we subtract off all the reactants. And really, maybe to avoid confusion, the way to think about this is instead of in terms of products of reactants, maybe you should just think about it as things going out and things going in. And that's actually consistent with our enthalpy table as well. Okay? All right, so let's expand out what this would be for our system. All right, so we still have this reaction term, so that's still the same. But now, at least in the outlet stream, what we have is the hydrogen, we have the oxygen, and we have the water, liquid water. H2O. And then in our input stream, what we have are the hydrogen, which makes up all of stream 1. And we have the oxygen, which makes up all of stream 2. Okay? All right? And so we need to figure out what each of these specific enthalpy terms, or the molar enthalpy terms, are. All right? But similar to what we saw with the reactive stream, we set our reference conditions for hydrogen and oxygen to be at 25 degrees Celsius and 1 atm. And those are the conditions, coincidentally, of the inlet and outlet streams. And so what that tells us we could do is we could just say these terms are equal to 0. All right. And so to calculate our delta H, the only things we need to look up are figure out how to calculate are the molar enthalpies of the hydrogen gas, oxygen, and water in stream 3. So at this point, I want you to pause the video and think about how you could calculate those terms. So to calculate the enthalpies of each of the species in the outlet stream, what we're going to do is what we did previously for non-reactive systems, is we're just going to integrate their heat capacities. All right. So for H2 gas, what we're going to do is we're going to integrate the heat capacity for hydrogen gas from the reference temperature, which is 25 degrees C, all the way up to the temperature of the outlet stream, which is 85. All right. And so this is the heat capacity of hydrogen gas, and we're integrating this with respect to temperature. I won't write out what the full form of this integral is, because if you look it up in the back of the book for the gases, they have those four. It's a really long polynomial. So if you integrate it, I'll just tell you what the final answer that you should get. Once you integrate it, you should get a value of 1.73 kilojoules per mole. All right. And it's a similar sort of procedure for the oxygen. Once you integrate it, you should get this value. And then for liquid water, same sort of thing. dt. Here you get 4.52 kilojoules per mole. Once you have these values, you can plug in those values to get delta H. Once you do, you'll see that your delta H dot, is equal to negative 181.941 kilojoules per second. Alright, so now we have what our delta H dot is. And so at this point, once we have our information, the next step we need to do is now we need to go to our energy balance and we need to solve it. Alright. The main new thing here is we now have an electric work term. So what I want you to do is I want you to pause the video and I want you to think about how we're going to incorporate that electric work term into our open system energy balance. To incorporate the electric work into our energy balance, it's actually pretty simple. All we're going to do is just add it to our open system energy balance. And so let's begin with our open system energy balance, which we know is delta H dot plus the kinetic energy term plus the potential energy term is equal to the heat rate plus the shaft work rate. And now we're going to add our electric work rate as well. We then need to identify which terms are negligible. So doesn't seem to be any big changes in the kinetic or potential energy in our system. Doesn't seem to be that much heat leaving the system. And there are no moving parts in the system either. So shaft work can also be assumed to be 0. And so what we're left with is delta H dot is equal to the electric work, which we know is 9.41 kilojoules per second. Okay? Now the problem, so we figured out what the electric work was, but the problem actually asks us for that work in units of kilowatt hours, right? And so kilowatt hours is not an energy rate anymore, it's just an energy term. And so what we really need is maybe just the shaft work, not a shaft work rate, or not shaft electric work, not an electric work rate. And to get that, we're going to take delta H dot times some time. Okay. Alright, so what we're going to do is we're going to take our delta H dot, which is in kilojoules per second, and we know that 1 kilowatt is a kilojoule per second. So that gives us kilowatts. And then we need to multiply by time, right? And since we're working with kilowatt hours, what we need to multiply by is 1 hour. Right? And we know that kilowatt hour is a kilowatt times an hour gives us a kilowatt hour. So what we're left with is 181.941 kilowatt hours. Right? And the reason we have a negative sign there is because that energy is leaving the system and is being used elsewhere. Okay? That's how you solve problem 1.